Dear students, this is our first lecture on stereochemistry, and in this series of lectures we will discuss some basic concepts of stereochemistry first and then some advanced topics in stereochemistry. And today's topic is CRAM'S rule, which is very important in the organic synthesis where we undertake stereoselective or stereospecific synthesis of different types of organic compound. Now, CRAM'S rule is basically for the asymmetric induction in case of alpha substituted acyclic aldehydes or ketones. So there, according to this rule, when in some non-catalytic reactions, the alpha substituted acyclic aldehydes or ketones, they will react in such a way that the diastereomer, which will be formed predominantly, that will be formed by approach of the entering group from the least hindered side of the aldehyde or the ketone, and the conformation of the aldehyde or ketone will be such that the nucleophile or the entering group will enter the aldehyde or ketone from the least hindered side. Means there are three groups present, say on the three substituents present on the aldehyde or ketone, which can be classified as S for small, M for medium, and L for larger group. So these are the three substituents which are present on the carbon, which is alpha to the carbonyl. Now, in such cases, the carbonyl group is presumed to react in a conformation where this larger group, which is present on the alpha carbon, is eclipsed with the R substituent of the carbonyl system. And in case of aldehydes, this R will be hydrogen, whereas in case of ketones it may be alkyl group or aryl group. And in such a conformation, the attack of the nucleophile is from the side of the carbonyl where the smallest group is present, rather than attack from this medium group. So the product will be formed predominantly by attack of the nucleophile from the side of the smaller group present on the alpha carbon of the carbonyl system. So this is called as CRAM'S rule. Now, in case of CRAM'S rule, few assumptions we make, and notable assumptions are there will be no distinction between ground state and the reactive conformations, and the postulate that conformation A makes a significant contribution to the ground state conformation is unlikely. And in view of this above one, the low rotational barriers around carbon-carbon bonds than more than one reactive conformation may be involved. This is as per the Curtin-Hammett principle, where the principle says that a ratio of the products obtained from a group of equilibrating conformer is determined by transition state energies, not by the concentration of the conformer. So therefore, the conformation A will make a significant contribution in case of product formation, and the attack of the nucleophile will take place from this side, and the product C will be formed as the major product in comparison to B product, where nucleophile is to attack from the side of the medium group. So that is how the predominant formation of this conformer is given by the CRAM'S rule. Then the substituent of the alpha carbons, they are classified merely with respect to the steric nature of those groups rather than any dipolar effect which are present in the molecule. So we will classify these as small, medium or larger group in terms of their bulk. That is how bulkier these groups are, and we are to ignore the dipolar effects which are present in the molecule. So this is a rather a big assumption which is made in the CRAM'S rule. Now we can explain few reactions on the basis of CRAM'S rules. For example, if we see the Grignard reaction of phenyl magnesium bromide with 2-phenyl propionaldehyde. So we can take this as an asymmetric compound also, that is we can use an enantiomer also, but we can use a racemic mixture also. So when this say racemic mixture here, what we have made is in the case of R enantiomer. So if this reaction is to follow CRAM'S rule, that means this will be the conformation in which this aldehyde will react with the Grignard reagent. And we know in case of Grignard reagent, this is the negative part, phenyl group is the negative part, or we can say the nucleophile which will attack the carbonyl group. So this nucleophile, if you see the conformation, the R group present on carbonyl here is hydrogen in case of aldehydes, and this is eclipsed with the larger group which is present at the alpha carbon, and largest group present on the alpha carbon is phenyl group. So this will be eclipsed with the larger group, and out of these two, this is the smaller group and this is the methyl group is the medium group. So as per CRAM'S rule, the nucleophile which is phenyl group will attack from the side of the smaller group, and that product formation will be predominating. So if you see this, the conformation of this methyl group is alpha, so behind the plane, so that means the nucleophile will attack from that side, that is from the side of hydrogen. So this will have this conformation, so therio product will be formed in 80% amount, and the other product formed is when the attack of the nucleophile will take place from the medium side of the substituent, and this will give rise to erythro product which will be formed in 20% amount. So this is how we can explain the formation of these two products in Grignard reaction of phenyl magnesium bromide with 2-phenyl propionaldehyde. Similarly, we can take another example. So this is lithium aluminum hydride reduction of 1,2-diphenyl propanone. If we take this as the reactant, and as per CRAM'S rule, the conformation of this during the this reactant during the reaction will be like this. The R group of the carbonyl, here it is phenyl group, so phenyl will be eclipsed with the larger group on the alpha carbon. So largest group on the alpha carbon is phenyl, so both these groups, they are eclipsed with each other, and now this is the medium group and this is the smaller group. So that means the nucleophile, and here the nucleophile in case of lithium aluminum hydride is hydride ion. So that means hydride ion will attack from that side of the molecule where the smallest group is attached. So the hydride will get attached to this carbon on this side of the molecule, and that is why you can see that conformation of this molecule or the product formed is this one, where both the hydrogens they are present on the same side. So we will get erythro as the major product, and this minor product in 20% amount is formed when the nucleophile will attack from the side of the medium substituent present at the alpha. Now, the limitations of the CRAM'S rule is, what we have assumed is that the starting materials conformation is where the alpha largest group present on the alpha carbon is eclipsed with the R group present on the carbonyl system, and because of the eclipsed conformation there will be an increased torsional strain across the reactant coordinate, and which is undesirable, and that is why this is a basis for a limitation for this CRAM'S rule. Then it has been seen that this CRAM'S model functions best when the larger group on the alpha carbon is a phenyl group, because that is having the lowest torsional strain in terms of the starting materials conformation. Then CRAM rule is also not able to predict that what will be the effect of increasing the steric bulk of the carbonyl system in terms of stereoselectivity. That if we increase the steric bulk of the carbonyl substituent, that is in case of aldehyde it is hydrogen, and if in case of ketones, say among the alkyl groups, it may be methyl, ethyl, isopropyl, tertiary-butyl. So as the steric bulk of the carbonyl substituent increases, what will be the effect on the stereoselectivity of different types of molecules? So there is no word from the CRAM'S rule that what will be the effect of increasing bulk in case of carbonyl substitution on the stereoselectivity of these types of molecules. So this is all about the CRAM'S rule, and these are the references which have been consulted for preparing this lecture. Thank you very much.